Let's continue. All right. I think we are at 6.4. We were talking about force, and this is a special kind of force which is called the impulse. Okay, so this is something happens at a very short time period. So you can imagine you use a hammer. Okay, to hit this one at time 4 or time 5 just for once. It happens almost within 0 time. Okay, and to quantify the force like this, what we can do is we define some function called delta function. Okay, so basically what we do is we define g delta t x equals 1 over 2 delta t for a minus delta t. So I need to put a somewhere. Let's just define this to be delta t. Yeah. Less than x less than a plus delta t. Okay. And it's 0 elsewhere. Okay. So basically what you have is you have something like this at a little bit before, a little bit after a. Okay, you have some function like that. And one thing you want to make sure is you want to make sure the integration is 1. From negative infinity to infinity, but basically from a minus delta t to a plus delta t. Okay, you want to make sure that. So now what you want to do is you want to let delta t goes to 0. Okay, then you can have something like this, and then even smaller. And what you want to make sure is you just want to make sure that still the total momentum or energy, it's just the integration, still equals 1. And finally, for the impulse, you just let delta ax equals limit delta t goes to 0, g delta t x. So basically, if I have to write it down, this one's infinity and the 0 at a elsewhere. So at a, it's basically infinity. But this infinity has been quantified to make sure that the integration of delta a is still 1. Okay. So this is something different than what we had before, because before we know, if you check the integration of something with a 0 length in the interval, you always get 0 regardless of your value. Okay, it's almost like from negative a to a, 3 dx, or whatever you put here, it's going to be 0 because you start from a, not negative a, from a to a. You start from a, you end at a. So of course, no matter what you put here, you are going to have 0. But this time we put something different, which is called the infinity. Moreover, we quantify such infinity through the limiting process. Then the whole thing becomes reasonable. Okay, and we use this to quantify the impulse force, which has a finite total amount. Meanwhile, it happens in almost 0 time. Okay. Before we go ahead and try to use this one for dpq, we talk about the Laplace transform of this delta A. X. Okay, and we did all the calculation all the way up to here. Let me write it down, the first one. It's technically from 0 to infinity. However, it's basically 0 everywhere except for here. So we can just do this. On that thing, we have 1 over 2 delta t. That's your delta times e to the negative st ct. We did all the calculation and ends up with this. Okay, some modifications here. I need a limit sign. Limit delta t goes to 0. And then we did several steps until we find we are here. And then we stopped here last time. Okay. Now, if you think about it, this is basically times what? What you see here is classic f 0 plus delta t minus f 0 minus delta t divided by 2 delta t. Limit delta t goes to 0. And that is the definition of difference quotient. So what we have here is f prime 0, where your fx is given by e to the sx. Okay, before difference quotient, we use h, but we use delta t. They are basically the same. All right, with that in mind, what is f prime 0? F prime x is s e to the sx. Therefore, f prime 0 should equal s. Therefore, this is s. So finally, this will be the Laplace transform of delta. So let me write it down. Should I use t or x? I use x. Okay, that works. Again, nothing surprising. This is some function we have seen before, e to the negative as. Okay. With that in mind, now we can deal with systems that involves impulse force. Let's try one example. Okay, it's called y prime prime plus 4y equals delta 0. G. Okay. y0 equals 0 and y prime 0 equals 0. Okay. So what's the situation here? Number one, it's undamped. There's no y prime. Moreover, without this impulse force, without impulse force, this spring is just sitting there. It's not moving. The initial position is 0, and the initial velocity is 0. So this one is basically not moving. Okay? Then what happened is, at time 0, you use a hammer to hit it. Okay. Moreover, the total momentum of the hammer is given by 1. That is represented by this delta 0. So it tells you, okay, the total amount is 1, and it happened at t0, 0. Okay. So what do you think is going to happen? Well, at that time, when you hit it, that thing starts to shake, right? And when this thing starts to shake, it never stops because it's undamped. So basically, by the impulse force, suddenly the whole thing shifted from static all the way to constant oscillating. That will be what happened to this spring if you hit it with a hammer. Okay? And that should reflect on the Laplace transform solution of this problem. So let's do it. Linear property. Good so far. S square L y plus 4 equals, what happened is e to the negative as for delta. Moreover, your a is 0. So this become 1. All right. Without the impulse, the right-hand side will be 0 because this is 0. Then you have no solution. Your solution is just y equal to 0. No oscillation, no anything. Stay there. With this impulse, now you have this. And that gives you okay, try to recall. This is the Laplace transform. Okay, so if you take the Laplace transform, you have 2 over s squared plus 2 squared, but then you times a 1/2, you have the 1. Okay, so this is how we got it. So finally, your answer is going to be before you have the delta function, okay, the whole thing stays steady. After you have the hit, the whole thing starts to shake constantly. All right. That's how we write down a system that involving the impulse force. And magically, that thing happens. That thing doesn't have a derivative. That thing should not have an integration. But somehow, through the definition of delta, now we can actually handle everything in terms of Laplace transform, even though that thing is very, very short. That thing is very special. Okay. Let's try another example. Y0 equals 1, and y prime 0 equals 0. Okay. What's going on? This is the thing. Okay. Number 1, it's dumped. Okay. Number 2, without impulse, what's going to happen is, at the first, this is 0, this one's at 1. No velocity, and then you'll just let it go. Once you let it go, this one is going to start to shake back because you are not having a 0 displacement. You have a force from the spring. Sounds good? So this one has a built-in frequency, and this one is going to shake back and forth. So eventually, the whole thing should be like this. Without the delta. Just shake and weaker and weaker and weaker. Okay. Now with this one, what's going to happen? You let this thing shake for 4 seconds. Then at time 4, you hit this one to the right by an impulse force with total momentum 1. Happens instantly. Okay, at time 4. So what do you think should happen to the whole thing? Then you should shake all the way up to 4, somewhere here. But then suddenly, this one got amplified. Actually, it's not amplified, it's a different direction. So let me take 4 is roughly probably here. Okay, 4. And suddenly this whole thing got amplified by that hit. And then you repeat this one again. Okay, so it's like a oscillation, weaker and weaker. Suddenly that thing got boosted at time 4, but then it started shaking weaker and weaker again. So eventually you go back to 0. Okay, now let's see how to do it in Laplace transform. Y prime plus 26y Ly equals L delta 4t. SLy prime minus y prime 0, which is 0, plus 2 is y0, 26 Ly e to the negative 4t s. Okay. Then what you have is s SLy minus y0 plus 2Ly minus 2, because this is 1, plus 2Ly. And this is also 1. So finally, s squared Ly plus 2 SLy plus 26 Ly equals this plus this plus s. Okay, now we have done this, so we know we need to complete the square, which is 5 squared. Okay. And we want to do a partial fraction. Okay. To give you some hint, number 1, we should look for something which is sine 5t. That one should produce, actually not sine t. That thing should produce omega. s squared plus omega squared, where omega is 5. That's what we should look for. Now you don't have it. You have a +1. Like we said, a +1 basically times e to the negative t here. Okay, so that is one component. We certainly need (5t). The cosine component. Okay. Finally, we need this. Okay. But modified by e to the negative 4s. Again, recall what we did before. Multiplying something with e to the negative 4s is the same as u4t times, and change everything to be t minus 4. Five t minus 4. Okay. With that in mind, it's not hard to see. This one equals that's this times 1/5 plus times nothing. So we have this plus another 1, but you need 5. So it's going to be 1/5. 5. Okay. So with the help of these facts, finally the thing equals 1/5 u4t sine 5t minus 4. Okay. Plus e to the negative t cosine 5t plus 1/5 e to the negative t sine 5t. Yep. Okay. So the Laplace transform of delta give you a e to the negative s. E to the negative s eventually produced this u4t. That means at time 4, the whole solution changed because you hit it with a hammer. All right. Hopefully the computation makes sense. For now, you're not so familiar with Laplace transform, so I gave you all the fact here. Okay? But eventually, when you get more and more used to those kind of things, you will realize it's nothing but a constant and an s term. All you need to do is just match the constant to make sure, that's why we need the 1/5 here and 1/5 here. But the majority should be okay. Okay. Delta produce e to the negative 4s. And we are familiar with the Laplace transform. If you have the Laplace transform, you times it with the e to the negative as. It's the same as multiplying a ut. Okay, so we did that too. Now let's look at the solution. Let's see my screen. Okay. So originally what we have is, we have this one plus e to the negative x sine 5x divided by 5. Okay, let's just focus on what happens at 0. So originally this is what we have for the oscillation without the impulse. Now, at this moment, what we did is we hit it with a hammer. Now we have the new solution. The new solution will be this one. Plus u4t times e to the 4 minus t okay, this is 4 minus x, all right, e to the 4 minus x times sine 5x minus 20. How do I do that again? Y is bigger than 0. No. No.
Dr. Chen, you can use the curly brackets.
So how do I do it?
You use, and then you can define your values.
Yeah, I did y bigger than, no, x bigger than 0. That's y probably. Still can't do it. How do I type them in?
Usually I do like an interval, like 0 less than. I'm not sure. You can mouse over the the error on the left and see what it says.
They think this is the point.
Yeah, I'm not sure.
More or less, it should be correct. Let's just Google it. Let's see. Y equals x. Yeah, that's what I have. A bigger than 0. 0 less or equal than that, less or equal than that. You can accumulate the conditions. Should I not include the comma? All right. Okay. Without the thing, the original thing should go like that forever. Now what I can have is this. Okay, so that's where this thing happened. Okay, so without the thing, this thing should just keep going, keep going, keep going, eventually just fade off. But now you just bounce it. This one actually redo everything again until that thing further bounce off. Okay, you can imagine the whole process because you have a friction, so constantly you're losing energy. What you did at time 4, basically you just added more energy to the system. Okay, but then eventually that thing just got faded away again. Okay. Moreover, if you check the solution you just computed, just by hitting something does not change the frequency. Originally, the frequency was 5. Now the frequency is still 5. Okay, so that is because you are not interfering with the period, only adding more energy to the system. All right, that's everything we need to do with impulse. It's just one concept which can quantify what's going on in the real time. The calculation will be similar, no matter how we do it. But now you can write down several systems that you cannot do before. Can you recognize what's going on here? Plus 5y equals delta 4t plus delta 2 delta 12t. So basically you have some oscillations, right? And then you hit it at t equals 4. You let it go for another 8 seconds, and then you hit it again at t equals 12. Okay, so you can hit whichever many times you want. You can hit it to the right. You can also hit it to the left. You just need to put a negative sign here. You can hit it with a total momentum 1. That's the default of delta. But you can also hit it with different momentum. All you need to do is just multiply the delta function by the momentum you want. If the integration of delta is 1, then if you multiply by 12, the total momentum is going to be 12. Okay, so you can hit it with different strength. You can hit it with different directions. Okay. Another interesting example people can think about is actually this. You take something which is periodic. So it's almost like you have a worker or a machine, and you can have some oscillation going from here back and forth to here. Okay. Now you put a hammer here. Okay. Which is rotating. So basically what this one does is for every single second, or maybe every 2 seconds, or every 4 seconds, this one just hit it. Forever. Okay, so that is going to be some other cases where you can have something just goes on forever, which hits with a regular pattern. And you can imagine it's not even hard to write it down. It's going to be y prime prime plus 4y plus 5y equals sum n from 1 to infinity delta NAT. Okay, which means you hit it. You hit it at t equals a, 2a, 3a, 4a, and 5a, and forever. Okay, those kind of cases is called periodic impulse. Can you imagine anything that behave like this? Periodically, you just have an impulse. Think about your heartbeat. You see those kind of machines to read your heartbeat. Your heart actually have an impulse for every fixed period. That's why you will try to read their diagrams for the impulse of your heart. You see something very similar to something we just draw on the Desmos. Usually that thing just fade away until you hit it again. And that thing just bump up and come back again. Okay. For your heart, of course, that thing does not go to infinity. Maybe for 70 years, 100 years, but you know what I mean here. Yeah, you can model your heart in this way. Very interesting. You can even add an injection to your heart strongly. Yeah, or things like that by using drugs, whatever. Okay. Is everything okay with the delta function? Computational wise, it's easy. I think the two key concepts for this is number one, how to define it in a reasonable way. Okay. Second, how do you do the Laplace transform? Okay. Finally, the last section, convolutions. QY. Okay. We are still thinking about signals or periodic functions, right? Harmonic oscillator. Okay. We did some examples where the right-hand side is not zero. We say it can be cosine something. It can be sine something. It can be e to the 5t something. Okay. Why? Because when we try to do the Laplace transform, PSY. What is PSY? Okay. Minus PY0 plus QLY. Equals. Now if I name this one to be FT, this is just going to be LFT. Mistake here. It's LYPS. Okay. Now what we can do is we can do this. And move everything to the other side. And finally, we have Ly equal this divided by this. The last step is try to do the Laplace inverse transform. Okay. From here, you can see several things. Number one, this term and this term really are not trouble because they're constant. So these two somehow is going to give you some term like this with a constant, of course, but we just say this, and some term like this with a constant. So this one goes to roughly cosine. This one goes to roughly sine. Okay, maybe you have to adjust it with e to the negative t. Maybe you have to adjust the w, omega, whatever. But these two terms were never the problem. So can you do the inverse Laplace transform? Really depends on what this is. You need to know what the Laplace transform of the force is. And that is a limitation. Because so far we only know several type of functions that we do know the Laplace transform. Exponential, we know the Laplace transform. Cosine, sine, we know the Laplace transform. UAT and delta AT. So if it's one of these five forces, we know how to write it. But of course, in real life, the forces can be anything. The force can be t squared. The force can be tangent t times e to the t. The force can be square root of t minus 1 divided by t squared. None of them actually we can go ahead and try to find the Laplace transform. It's going to be difficult. Sounds good? So what we want here now is we want a general inverse Laplace transform for this, regardless of what kind of f you have. We can always do it. Okay, we want this for any f. Even if sometimes we don't even know the Laplace transform of f, we should be able to do it. Okay. So let's think about how to do it. You want the inverse Laplace transform of this. All right. We can further decompose this one. This is hard. This is easy. Okay, this part goes to sine. Okay. Then the key part is how do I get the inverse Laplace transform of the multiplication of two Laplace transforms? Okay, because I know this one, and this one is nothing but another one multiplied with this one. So let me write it down in words. The key becomes we need to know how to find L inverse Fs GS, the multiplication of these two. Or more precisely, if L F equals Fs, okay, Lg equals GS, then together, what is L inverse F times G? Or we can say L what equals Fs GS. That's what we're looking for. Moreover, of course, this one should be in terms of F and G, somehow put it together. We just don't know how to put them together, but they should be only affected by F and G. Okay, think about it. For this case, you know everything about G. You also know everything about F because you're looking for L inverse L Ft. Of course, it's determined by F. But now is, what if I multiply these two in the range together? Will the original thing be just a simple multiplication of F and G? Or is this something more complicated? Okay, but nonetheless, this is what we're looking for. Okay, another way to think about it is, here is F and G, Laplace transform. Here are F and G. We know if we do F plus G here, we simply just do F plus G here. That's the linear property. Now the problem is, if I just do F times G here, is this simply just F times G here? And you can verify it's not. It should be some other thing. Okay, now we're looking for what is that other thing. That's what we're looking for. Okay, we will show this is actually another type of multiplication, quote unquote, which we call convolution. Okay, so convolution of the original signal is the same as multiplication of the Laplace transforms. That's what we're looking for. And it's not simply just multiplying these things together. Okay. With that in mind, let's define what a convolution is. Actually, let's derive it, not define it. Okay. Let's see. What we want is something defined by F star multiply G, which is called convolution. The property we're expecting is, if you convolute these two things together, and then you do the Laplace transform, it's the same as doing Laplace transform of this and the Laplace transform of this together, and then multiply them. This is what we want. Then if you know these two and their inverse, you will know how to put both of the inverse together to produce this convolution. That's what we want. All right, so let's start from here. Okay, our goal is we know this equals that, then everything is settled. dt. Okay. This time you cannot use t anymore. To stay out of confusion, we can use u. Okay. Now what we can do is we can put them together. Oh, take it back. I'm missing one. Another one. Okay. Now f t g u dot e to the negative s plus t plus u d u dt. Okay. Now remember, we are trying to show this one equals some Laplace transform of something, which is something times e to the negative st. But what we have here is t plus u, so we can do a change of variable. Name tau equals t plus u. Then t is nothing but tau minus u. So the whole thing becomes f tau minus u gu dot e negative s tau du d tau, because d tau and dt are the same. U is still from 0 to infinity. This is from u to infinity. Hold on. Let me see. Tau is t plus u, no problem. If t goes from 0 to infinity, this one should be from u to infinity. No problem. Yeah. And then let's switch the order. T tau du. And to put this one in, tau, hold on, d0 and u here. I miscalculated. It should be from 0 to tau. But somehow I did it from tau to here. Zero to infinity. Yeah, of course it's this. All right. Tau to here, tau to here, tau to here, tau to here. Minus u s tau. I want this. This is what I want. E to the minus s. Hold on. F tau minus u g u d u. e to the s tau dot out. Either way, I think I did the right thing so far. Worst case, I just redo it. Let me keep this and do the integration. I treat it, no, it can't be. I skipped one step in my notes. Now I'm confusing myself. Well, we have 5 minutes left. I would say let's stop here. Next time I will recheck my notes and make sure this is correct. So far, dt equals d tau here. Change that to this, change that to this. U from here to here, so far so good. This changed to tau, s tau. T equals tau minus u, so far here, okay? Finally, tau goes from u to infinity. So far it should be correct. So there must be something wrong in the steps I write down in my notes. Okay, that's all for